Hi everyone, welcome to the series on feature engineering for data science and machine learning. In the previous few videos, we touched upon some of the filter methods like variances, low variances, covariances, and correlation. We will continue to discuss few other methods in the category of filter methods. Just to recall, feature selection methods especially focus on understanding individual columns and deriving descriptive statistics on the columns. Thereby, we are in a position to understand the column and make a decision if we want to keep those columns or remove irrelevant columns. Essentially, feature selection methods help us to come up with a reduced set of features for our machine learning. So in the previous videos, we talked about variances, covariances, and we looked at why covariances are important. We also looked at correlation, and in terms of the side effects of correlation within the predictive variables, we looked at multi-collinearity assessment. Today, in this video, we'll talk about the various types of correlation that are applicable typically in a data science and machine learning projects like Pearson's and Spearman and Kendall. Okay, so let's talk about types of correlation and for specific data type. Essentially, why we need to learn about the various types of correlation. We have various scenarios. For example, we could be dealing with continuous variables. We could be dealing with data which is linear or non-linear. We could be dealing with data which is ordinal and still be linear or non-linear. We could be dealing with data which is ranked data. Now, each of these situations I've categorized. If we have continuous variables and they exhibit Gaussian pattern and linear relationship, we use Pearson's correlation. If we have ordinal data and they have rank and they have linearity or non-linearity, it can be Spearman correlation coefficient can be used. But typically it is used when we have non-linear variables. Kendall tau is used for mostly categorical data. So this is the reason why we need to understand these three types of these three popular types of correlation coefficient. There are many other correlation coefficient methods. The Pearson's is a measure between association of two variables, two continuous variables, and the values range from -1 to +1. As you recall, in our previous session, we talked about it. Why it would be so? Because correlation is nothing but covariance as a numerator, and you divide the covariance with the standard deviation of x and y, and that gives you a normalized or standardized value between -1 and +1. -1 and +1, both the extremes considered as strong indicator, whereas 0 is considered no association or no correlation. And this is suitable for data which is linear relation and has a Gaussian pattern. On the other hand, Spearman rank correlation, it is used when we have a non-linear relationship within the variables, and this is based on rank. Compared to Pearson's, this is something somewhat different. We use the rank orders of the data values rather than these exact values. And again, the range is -1 to +1, and it is suitable when we have non-linear data, and it could be used when we have continuous or ordinal as well. Spearman correlation is used when we have data which is not having a linear pattern, and it is based on the rank of the values. I think we already talked about most of it. I just summarized some of the main points, but Spearman can be used for both continuous and discrete. And essentially, the formula is the rank of x and y, and you compute the covariance, and then you divide it by the standard deviation. Pretty much similar to what we saw in our Pearson's method, just that the difference is the date is not about data, but about the rank of the data values. Kendall tau, on the other hand, it is good for categorical data, and this also measures the strength of association and the direction of association. It's similar to Spearman, but it uses a couple of new formulations, you can say, like concordant data and discordant data. I'm going to show you an example of what is concordant and discordant. And once you know the number of concordant pairs and discordant pairs, you apply Kendall-Tau formula. And the output of the formula is again -1 and +1, and -1 and +1 being strong indicators, 0 means no association. It is often used when you have ordinal data. I'm going to show you the use case where you actually use Kendall-Tau. Now, what is concordant and discordant? If you look at the values here, x, two values, a and b, that means the is in a time event, let's say the value is 2, and the next time event, the value is 1. The difference is 1, positive 1. Similarly, the y column has a value, again, 4 and 2. So difference is 2. Now, look at these differences are positive. So when the differences are same direction, like positive or negative, we call that as concordant. That means the change in variable x and variable y, it is happening in the same direction. Whereas if it is one of them positive, one of them negative, then we call that as discordant pair. Let's look at some examples here. Let's say the data series 1, 2, 3, 4 and 2, 1, 4, 3. Okay. Again, so whenever the changes are in the same direction, we call it concordant. Whenever the changes are in opposite direction, that's discordant. So let's put x, y, and these are the values. Let's look at 1 and 2 and 2 and 1. If you notice the change between x and y is in a different direction, so that would be discordant. And look at the other pair here again. The previous one is the change is 1, and here is in the opposite direction. So that's why it is discordant. If you look at the other here, 1 and 2 and 3 and 4, the change is in the same direction. So that is concordant. And likewise, you're going to look at all the pairs and then eventually compute the instances where you have concordant pairs and where you have discordant pairs. Count the number of concordant pairs and discordant pairs, apply this formula for Kendall-Tau. This will result in value between +1 and -1. So interpretation is pretty much similar to like Pearson's and Spearman. I'm going to show you a Python code demo where I'll show you the specific characteristics of Pearson's and also Kendall-Tau. Let's look at the Python implementation, dummy implementation, to show you what is Pearson's. It's used for continuous data and when you have linear pattern. So NumPy is the package that I'm going to use. You can use pandas also to compute Pearson's correlation, or you can use custom Python function. Let's say these are the two variables, and NumPy provides you covariance function, which allows you to compute the covariances here. And similarly, it also allows you to compute the correlation coefficient. Notice here, it is a perfectly aligned, association. Hence, you get -1 and -1. That means this is an opposite direction. Pearson's correlation, let's generate some random data and associate that with some target variable. And here, you notice here the positive correlation between x and y. Negative, again, simulate some data and put minus here, and that would be your negative. No correlation, just generate some random data, two pairs, x and y, and notice here the correlation coefficient is pretty weak. And in the plot, you can see it is randomly scattered in both the directions. That means there is no pattern. So correlation matrix is possible using data frame, column 1, column 2, and then you can compute here these are the columns, and then you look at the pair plot and see which pairs give you a strong linear pattern. For example, this one is pretty strong, this one is strong, this one is strong, this one is strong, this one is also strong in the opposite direction, but the others are not strong, they are randomly scattered. So this gives you a view which column to keep and which ones to remove in your model preparation. Now, Pearson's correlation is not good when you have a non-linear pattern. Let's say some random data, and I've generated a random data here with the y being a cube of x, that means some polynomial. transformation, and you see here this is nonlinear pattern. I'm going to apply here the correlation method, Pearson's and also Spearman. Notice here the coefficient is 0.93, which is lower than Spearman. That amplifies the fact that if you have a nonlinear pair, it's better to use Spearman correlation coefficient than Pearson. Impact of outlier, this is also evident. Let's take the data series here, X and Y, and infuse some outlier, just 1 point. You can infuse many other outliers, and you can see the effect. So this is my outlier point in this nonlinear pair of data. And then you compute Pearson's and Spearman. Notice because of the outlier, Pearson's has gone down even further and Spearman is pretty okay. So that also amplifies the fact that if you have outlier, if you have nonlinear data, it is good to use Spearman correlation. In the next example, I'm going to show you Kendall tau and where to use Kendall tau. Okay, so let's take a look at where to use Kendall tau. Let's take a use case here. We have a basketball team and there are two coaches, and these two coaches are ranking their players from worst to best. Means they are going to assign some number 1, 2, 3, 4, 5, and the other coach is also going to do the same. And you would like to find out if the ranks provided by coach 1 and coach 2 they are in agreement or they are consistent. So the objective of the system here is to find out if the coaches agree with their ranks, whether you have a ranking consistency or not, whether the coaches are applying a consistent method of ranking or not. You can also find out some patterns in the ranks if you compare a few coaches ranks on the players. Overall, is going to build a robustness of ranking system. So use the SciPy package, which provides you Kendall tau, and let's say you have coach 1 and coach 2 rank. Simply apply Kendall tau, and it's going to return you here the value, which is zero point 0.9, which means these coaches agree with each other perfectly. 0.9. Some other use cases of Kendall tau, let's say the talent show judging, and let's say you have few participants and there are 4 or 5 judges, and these judges are going to rank those contestants, and you can compute the Kendall tau between a pair of judges, A and B, A and C, B and C, and then you can see which pair of judges they align with each other, which ones don't. In this case, all of them align or agree, although not very strongly. A and C is pretty strong, but the A and B and C are not so strong. This is the use of Kendall tau. Let's take one more use case. We have stocks, few stocks, like 5 or 6 stocks, and there are rating agencies which are rating these stocks. Okay, and then you apply here the Kendall tau between the pairs like A and B, A and C, and likewise. And you can make some decisions whether so the rating agency A and B they differ. That means there is some problem in terms of whatever. It could be the ranking system, it could be the idea that they have, or their knowledge about the stocks. It could be any other reason. A and C are positively aligned, but not very strongly. So these are the use cases where we apply Kendall tau. So just to summarize which one to use when, I'm going to show you another slide. We talked about these three methods, Pearson, Spearman, and Kendall tau. Let's see which one to use when. Pearson's correlation is good when you have linear relationship between the two continuous variables and data have some assumptions of normality. Normality means Gaussian pattern. So in a perfect numeric situation where we have a Gaussian pattern and linearity, we use Pearson's correlation. Spearman is typically used in both the cases, but mostly it is used when you have discrete and nonlinear pattern. Kendall tau is definitely used when you have a nonlinear data and rank and ordinal data. Kendall tau is not used when you have continuous data. Spearman can be used when we have continuous data as well. So in the next video, we'll talk about information value method, which is another filter method to understand the relation between predictors and the outcome variables. See you in the next session.